All right, we covered the nomenclature of amines, and now we're going to get into properties of amines. Some you'll know. For example, you know that the nitrogen atom in a typical amine is sp3 hybridized. We have the lone pair in an sp3 hybrid orbital. The bond angles are close to 108, right? As long as you understand that they're going to be a little less than 109.5 degrees. This is something you should have covered in General Chemistry 1. And it's just because that lone pair pushes the groups down a little bit like that. So nothing really new there. It says the carbon-nitrogen bond lengths are 147 picometers, which is slightly shorter than a carbon-carbon bond and a little bit longer than a carbon-oxygen bond. And that makes sense because as we go across the second period, right, we know that atomic size gets smaller and smaller as we go from left to right across the second period. And then it says here, under what circumstances would you have a nitrogen that's sp2 hybridized? Well, that kind of brings us to something that we would have discussed in chapter 1, okay, of Organic Chemistry 1, and that would be in an amide. If you look at an amide, okay, you might look at an amide and say, well, that nitrogen has 3 bonds and 1 lone pair, therefore it's sp3 hybridized, but in fact it isn't. Okay, the nitrogen in an amide is actually sp2 hybridized. And why is that? Well, the reason we know that is because that nitrogen is participating in resonance. And if the nitrogen is participating in resonance, and we look at the other contributor to the resonance hybrid, which looks like this, okay? Well, in that case, you can see that the nitrogen clearly is sp2 hybridized. So the question is, well, is it sp2 or sp3? Well, the answer is it's sp2, right? It has to be sp2 in order for there to be a p orbital on this nitrogen has to be sp2 hybridized, right? And the only way you can have resonance is to have a continuously overlapping system of p orbitals. So again, that was covered way back in chapter 1 of Organic Chemistry 1. So if you need to go back in the book and review that, I would go take a look at that. So if you have 4 different groups attached to a nitrogen, a lone pair and 3 different R groups, is it a chiral center? And the answer is, yeah, technically it is, right? Because you've got 4 different groups attached to an atom. So technically it would be a chiral center. So if you're wondering, well, why don't we look at nitrogen and consider it to be a chiral center if you have some kind of, you know, tertiary amine or secondary amine or where you have 3 different R groups? And the answer is the amines are not optically active. Okay, and why are they not optically active? The reason why is because they invert to both of these, I guess you could call them kind of stereoisomers, they invert via this trigonal pyramid really rapidly. So pyramidal inversion occurs so quickly and the barrier of rotation is so low that you get a mixture of both, and so the amine simply wouldn't be optically active. It passes through this trigonal planar transition state. But that's why we don't consider amines chiral compounds, if you've ever wondered that, even though the nitrogen can be attached to 3 different groups. It's because pyramidal inversion, the barrier of inversion is so low. Nothing more than that. All right, let's talk a little bit about hydrogen bonding. And I know that you know a lot about hydrogen bonding at this point in your career. But if you have an amine with less than 5 carbons, typically we consider those amines to be soluble in water. So let's say you have something like, you know, diethylamine, you know, or ethylamine, that's definitely going to be water soluble, or propylamine, right? That would be water soluble, etc. As long as you have less than 5 carbons. Now, primary and secondary amines, I mentioned this already, that they can hydrogen bond, right? Because here we have a primary amine, here we have a secondary amine, and in both of them we have nitrogen-hydrogen bonds. But in a tertiary amine, we have no hydrogen bonding because the nitrogen has no hydrogen bound to it. Now, if we look at the boiling points or the boiling point trends as we go from an alkane to an amine to an alcohol, right, that all have similar molar masses, you can see that the boiling points increase. And the reason why is because when we have an alkane, the only intermolecular force that it would experience would be London forces. Then we go to an amine and an alcohol, and of course they both have hydrogen bonding, but the hydrogen bond in an amine is going to be a lot weaker than the hydrogen bond in an alcohol. And the reason why is because nitrogen is not as electronegative as oxygen. It's nothing more than that. What else? So we've covered the boiling points of an alkane versus an amine versus an alcohol. We've covered the boiling points of primary and secondary and tertiary, maybe not exactly. But if you look at the primary and secondary, they can participate in hydrogen bonding. And so they have much higher boiling points than the tertiary amine, which has no hydrogen bonding, so no H bonding. And so even though it's an isomer of the other two amines, the propylamine and the ethylmethylamine, it has a boiling point that is much lower. And again, it's because of lack of hydrogen bonding. All right. What else? It says many small molar mass amines have unpleasant odors, like methylamine, for example, or trimethylamine. Those smell like rotten fish. So if you've ever learned of trimethylamine, and we talked about this compound earlier, it has a very fishy odor. And what happens is human beings actually make trimethylamine in their body, and the thing is that if you don't have the flavin-containing monooxygenase 3, which converts the trimethylamine to the N-oxide, which is this compound here, then that would produce what's called fish odor syndrome or fish odor disease. You can Google that if you want to, but it would be a pretty horrible thing to have. Also, you've probably heard of these compounds here, putrescine and cadaverine, right? You've heard of the word putrid and cadaver if you've ever smelled a cadaver. So if you've ever gone to a grocery store and they're cleaning out the fish counter and you smell rotten fish smell, well, that's going to come from amines. So amines have terrible odors, or some of them do anyway. It says here that amines are stronger bases than alcohols or ethers. So amines are proton acceptors, right? They're bases. They're weak bases. However, they are bases. They're not strong like hydroxide or butyllithium or something like that, but they are bases. So amines are organic bases. I want you to keep that in your mind. Let that be a mantra. Amines are bases. Amines are bases. So if we take an amine and we put it in the presence of a strong or a weak acid, it's going to be readily protonated. So let's say we take triethylamine here and we put it in the presence of a carboxylic acid like acetic acid. What we end up with is the triethylammonium ion. So you would call this the triethylammonium ion. Okay? And that has a pK of around 11. Well, which side is the equilibrium going to lie to? Well, if this is our base, this is our acid, this is our conjugate acid, and this is our conjugate base, the equilibrium is always going to lie to the side of the weaker acid. So it's going to lie to this side over here. And then we see that manifest in the arrows right here. Now, it's a good idea to have a general kind of knowledge of the pKa values of protonated amines, right? And the reason we deal with protonated amines is so we can think in terms of pKa values. So let's take a look here. It says here pKa values, table 22.1, of the ammonium ions of several amines. So if you take a look at all of these amines, so we start with methylamine, ethylamine, isopropylamine, cyclohexylamine, dimethyl, diethyl, trimethyl, triethylamine. Every single one of these protonated amines, they all have alkyl groups, right? These are all alkylamines, right? Alkylamines. And they all have a pKa what? In the same range. They're all around what? Pretty close to 11, as a matter of fact. I mean, this one is around 10, but they're all 10 to 11-ish, right? Something like that. So a pK, 10 to 11 for any kind of alkylamine. Now, what do we know about pKa? We know that the weaker the acid, the stronger its conjugate base. Therefore, the stronger the acid, the weaker its conjugate base. And if we look at the pKa of protonated arylamine, so protonated aniline derivatives, so we would call this an anilinium ion, you can see that their pKa's are much lower. So that means that all of these are stronger acids than alkylamine. So if it's a stronger acid, that would mean that the deprotonated form, this form here, would be a weaker base than an alkylamine. Does that make sense? It makes total sense. Right? It makes sense based on resonance. If you just compare an alkylamine, let's say you take ethylamine, for example. Ethylamine, which is an alkylamine, which is on the previous slide. Right? If we protonate that, right, we get the alkylammonium ion. And if we go over here, we see that ethyl ammonium ion has a pKa of around 11. So we'll just put here pKa pKa is equal to 11-ish, right? And then if we compare that to the anilinium ion, this is much more acidic. So that means that this is a weaker base. Now, why would aniline be a weaker base than ethylamine? Well, the lone pair on ethylamine is localized, right? It's just sitting there. It's not going anywhere, so it's always available for protonation. Whereas if we were to draw aniline, and everybody should be able to do this, and I'm not going to draw all the resonance forms, but you should be able to draw the resonance forms of aniline that show the lone pair delocalized inside the ring. And so since the lone pair in aniline is delocalized, that means that it's not just sitting there on top of that nitrogen, it's delocalized throughout the entire molecule, and therefore it's not as readily available to be protonated. Therefore, aniline derivatives are going to be weaker bases. So when you protonate them, they produce stronger conjugate acids. Give me a thumbs up if you're like 60% of the way with me on that idea. You'll probably have to read that yourself to fully understand what I said, but hopefully you understand it now. Now, if you look at a really cool example here, if you look at pyrrole, pyrrole is an aromatic compound and pyridine is an aromatic compound. But when you protonate them, their conjugate acids have a vast difference in pKa. Now, why would the pyrrole, the conjugate acid of pyrrole, why would this be so much more acidic than the pyridinium ion, than when we protonate pyridine? Could anybody answer that? It's not really about stability. It's about aromaticity, right? So this is an aromatic compound. So let's do it like this, okay? Pyrrole is aromatic. Pyridine is aromatic. The thing is, when you protonate pyridine, you still get an aromatic compound, right? This is perfectly aromatic. But when you protonate pyrrole, the nitrogen is now sp3, and this is non-aromatic. So you take something that's aromatic and you convert it to something that is non-aromatic. Does that make sense now? Right, so that's why pyrrole, it's pyrrolidinium ion is so much more acidic than the pyridinium ion. I'll try to stop saying that. It's kind of a tongue twister there. Anyhow, so you should have a general idea of those pKa's and where they come from. So we've already covered the solubility of amines. And of course, we can enhance the solubility of an amine by treating it with aqueous acid, right? When we saw that earlier, right? So for example, let's say we took, I don't know, diethylamine, okay? And we treat that with HCl. Well, diethylamine has 4 carbons in it. Is it going to be water soluble? I suppose to some extent. But if we put it in a strong acid, then you're going to end up with the diethyl ammonium ion, right? Plus here, and then we get Cl minus here. So we end up with a salt, right? And we know that a salt is going to be more water soluble than the free base. We would just call this the free base. Free base, right? The salt is going to be more water soluble. And so we can extract an amine from organic impurities by adding aqueous acid and converting it to the corresponding ammonium ion. All right, so that's one of the techniques we can use to purify mixtures of organic compounds. If you have an amine in there, you treat it with aqueous acid, and that's going to go into the aqueous phase, whereas the organic compounds that aren't salts are going to go into the organic phase. Now, going back to this whole idea of making salts, the reason that a chemist has to understand that very well is because lots of drugs are actually marketed as salts, and you can see some examples here. So you see this compound here used to treat hypertension and anxiety, and then you've got Gleevec. So Gleevec is a very famous cancer drug. It's not as famous as Viagra, but it's still famous in its own right. So you can see that all of these compounds are marketed as salts, and there's good reasons for that. So we've covered the pKa of the conjugate acid of most alkylamines and arylamines. I already explained this to you earlier on. This is just a rehash of something I told you before, that the lone pair in an aniline derivative is delocalized, and therefore anilines are going to be less basic, and therefore they're going to produce stronger conjugate acid. So if we look at the conjugate acid of a bunch of aniline derivatives, you can see that if you put an electron withdrawing group, right, this is an electron withdrawing group, that's going to increase the acidity of the conjugate acid. Why? Because it's pulling electron density away. So it makes this lone pair even more delocalized. So if it's less basic, that means you get a stronger acid or stronger conjugate acid. All right. So you should have an understanding of what's going on there. And then, of course, if you have a methoxy group, well, that's an electron donating group by resonance. It is electron withdrawing by induction, but it's electron donating by resonance, and you should be able to draw the resonance structures here. I'm not going to go over all of those, but that's why the pKa of the conjugate acid of paramethoxyaniline is higher than that of aniline. So you should have an idea of how electron withdrawing groups and electron donating groups mitigate acidity. So again, if we have an electron withdrawing group, that's going to decrease the basicity or increase, and we'll put here, therefore, increases acidity of conjugate acid. There we go. All right, now the lone pair of an amide. Let's just go over this one more time. Okay, we've already talked about why the nitrogen in an amide is sp2 hybridized, and that means that that lone pair is delocalized, right? Because it's in an unhybridized p orbital, right? You have a p orbital here, p orbital here, p orbital here, and we need those in order to have resonance. And so if that lone pair is not localized, it is delocalized. It says here extensively delocalized. That means that it is not available for protonation, and therefore the lone pair on an amide is not considered to be basic. So an amide is not a base. It's not a nucleophile. Amines are bases and amines are nucleophiles, but amides are not. Now, going back to a little biochemistry here, if you think about physiological pH, which is pretty close to 7.3, amines are generally speaking going to exist as ammonium ions, right? If you take an amine and you put it in the body, okay, which is a pKa or pH of around 7.3, so we'll just put here 7.3. Well, we saw that the pKa of the protonated form of an alkylamine is going to be 10 to 11. So the equilibrium is going to lie to the side of the weaker acid. And that is why amines, generally speaking, are protonated at physiological pH. I'm not going to review the whole Henderson-Hasselbalch thing. We could go over this maybe another time. But for now, let's just, maybe I'll bring this up next class. So remind me to go over Henderson-Hasselbalch with you if we have time. The last class. I don't know if there might be a question about that on the homework or something, but we need to get into synthesis. So let's take a look at a couple of problems here and see if we can solve those. So the first question is rank these compounds in order of increasing boiling point. So you can see I've got a tertiary amine here, I've got a primary amine here, I've got a secondary amine. Could anybody tell me which one of these is going to have the highest boiling point? Would it be the primary, secondary, or tertiary? Absolutely. It's going to be the primary one, isn't it? Right? Because it can do the most hydrogen bonding, followed by the secondary, and then followed by the tertiary, which is going to have the lowest BP. All right, 22.5. Identify whether each of the following compounds is expected to be water soluble. So what did we say? We said if we had less than 5 carbons per amino group. So here we have a total of 8 carbons. And we only have 1 amino group. So what do you think, yes or no? Exactly. Thanks, Maria. The answer is no. What about the second one? We've got 3 carbons and 1 amino group. I would say yes for that one. It's less than 4. And then for the last one, we have a total of 6 carbons, but we have 2 amino groups. So it's like you have 3 carbons for 1 amino group and 3 carbons for the other. So I would say yes for this one. Yep, absolutely. Absolutely. Let's try something that's maybe a little more complex. It says for each of the following compounds, identify which compound is the stronger base. So the compound that's going to be the stronger base, I'll put here, lone pair is localized. Therefore, not Therefore, it's not going to be participating in resonance. So if I take a look at these two here, I'm going to put this lone pair in red, and I'll put this lone pair in blue. Could anybody tell me which lone pair is going to be a stronger base, the pair in red or the pair in blue? The ones in red, right? They're not participating in resonance. The pair in blue is participating in resonance, aren't they? So the answer is going to be the first compound. Is going to be a stronger base. All right. Now, it's not always tied to resonance, is it? Right, if I put this lone pair in red and I put this lone pair in blue, right, which one is going to be a stronger base here? Well, this one is going to have something to do with aromaticity. Because if I protonate the one in red, I'm going to end up with my pyrrolidinium ion, where I destroy the aromaticity, right? So I go from something that is aromatic to something that is non-aromatic, all right? Whereas if I protonate the second one, we can see that this compound is non-aromatic to begin with, right? This is a I'll just put it in blue maybe. This is a non-aromatic compound anyway. And so the lone pair is not functioning in anything to do with aromaticity. And so this one is going to be a stronger base, right? The lone pair is going to be just localized, all right? Whereas the lone pair in the first one is participating in aromaticity. All right, the next one might be a little less complicated. If I put this lone pair maybe in green, and I put this lone pair in black, which one of these lone pairs is going to be more basic? The green one or the black one? Yeah, exactly, the green one, right? The green one is going to be the answer. And the reason why is that lone pair is localized. We see the lone pair here is definitely not localized. And the last one is kind of like the difference between pyridine and the pyrrole, right? So if I protonate, right, this ring is aromatic, but then if I protonate it, right, then it becomes non-aromatic. But this one, if I protonate it or don't protonate it, it's still aromatic no matter what. And so based off of that, I'm going to erase all that spinach. Oops, I'm trying to delete it. So based off of all of that, right, this is going to be a stronger base, okay? Because it doesn't matter if you protonate, it's still aromatic. So we'll put here aromatic, even when protonated. So that means that lone pair is available. Whereas this lone pair, put it in blue maybe, this lone pair, we'll put here required for aromaticity. And so if you protonate that lone pair, you destroy the aromaticity. Give me a thumbs up if you're with me on that. Maybe 75% of the way? All right, cool. All right. Usually students do very well at that, kind of identifying a stronger base, stuff like that. In terms of increasing basicity. So really all we're doing here is we're just kind of examining the lone pair. So if I put this lone pair in blue, this lone pair in red, and I'll put this lone pair in black. Which one of these lone pairs do you think is the least available? The blue, the red, or the black? It's the red ones, right? Because you've got electron withdrawing groups. You've got the bromine, which is electron withdrawing via induction, and then you've got the carbonyl here, which is electron withdrawing. Okay, so if we go strongest base, strongest boost, and then we have weakest base, weakest base. We're going to put, so we'll put red down here. Okay, and which one of these is going to have an electron donating effect? If we compare the black one or the blue, which one's going to have the most electron density donated to it? You might have to think back a little ways, but our groups are actually electron donating groups via hyperconjugation. And so that means that this one, since it's got electron donating groups, the black one is going to be the strongest base. And then you have the blue, which is going to be somewhere in the middle like that. All right, there you go. So electron donating group. And then here I should have put electron withdrawing group, something like that. Okay, there we go. So we've covered properties of amines. Let's get into some synthesis and some reactions here. This is kind of where the rubber meets the road, where we get into some reactions. And we only need to review a few before we're going to get to practice. So let me just check one quick thing here before we move on. All righty. Okay, where are we? I'll stop singing. Here we go. Okay, so let's do a little review on ways to make amines. How do you make an amine? Well, these are some ways that we've learned already. The first thing is the reduction of a nitrile. You remember that a nitrile is made from a cyanide. So if you take sodium cyanide, right, which is this compound, and you treat it with a primary alkyl halide, it does nucleophilic attack, loss of leaving group, an SN2. You make a nitrile, this is called a nitrile, and then you reduce it with lithium aluminum hydride, and that makes an amine. So you make a primary amine. Okay, so that's one way we learned to make an amine. Another way that we learned was from a carboxylic acid. So if we take a carboxylic acid, make the acid chloride, right? So in step one, we end up making the acid chloride, okay? Then we treat it with excess ammonia to make the amide. So this is an amide. And then we reduce the amide with lithium aluminum hydride, followed up by treatment with water. And we end up making a primary amine. Now you notice the difference between the two methods. In the one on the top, or the previous slide, you end up adding a carbon. Whereas in this version here, where you start with the carboxylic acid, the carbon skeleton is unchanged. So you're not adding any carbons in this situation. All right. Another way that we saw how to make an amine was to reduce a nitro group. When we talked about electrophilic aromatic substitution, so this would be chapter 18, we learned how to do a nitration of an aromatic ring to make nitrobenzene. And then we said, well, you could reduce it via hydrogenation. So this is hydrogenation, or you can do reduction. And a couple of methods that we saw in chapter 18 was to use iron or zinc reduction, but you can also use tin, or you can use tin 2 chloride. So this is tin 2 chloride. And if you're wondering, well, why would I need tin 2 chloride if all the other things work? Why would I get some kind of tsatzy reagent? Well, the reason why is that tin 2 chloride is very mild. So mild conditions. And that way it avoids reducing other groups. And then, of course, since you're an aqueous acid, you actually end up making the aryl ammonium ion. So you treat it with base, and that deprotonates. So that gives you your free amine. All right, so with each one of those in mind, let's see if we can come up with a way to make these. So let's see here. Draw the structure of an alkyl halide or a carboxylic acid. So we'll just do maybe the first one. So alkyl halide or carboxylic acid that might serve as a precursor in the preparation of these amines. So if we want to make, so this would be 1-butanamine, or you could call it butylamine, either way. I'm talking about this compound in A. So if we wanted to make it from an alkyl halide, what would we need? We'd be using sodium cyanide in that case. So we would want propyl iodide, like this, and then we would treat it one with sodium cyanide. Maybe I should just put the intermediate here. So it would give us 1, 2, 3, and then we have our nitrile, and then we're just going to reduce that with lithium aluminum hydride. So 1 is LAH, 2 is H2O, and that will give us our product. Okay, whereas if we want to do it from a carboxylic acid, in that case, we'd need a 4-carbon carboxylic acid, so butanoic acid. In step 1, we're going to treat it with thionyl chloride. That makes the acid chloride. Step 2, we're going to treat it with excess ammonia. That makes the primary amide. And then in the last 2 steps, we just reduce it with LAH and then treat it with water for the workup, and that gives us the product as well. All right, so what I'd like you to do before the next class is to give B and C a try. So we're going to do B on Wednesday in class. We'll give that one the old college try. All right, so let's move on to some new reactions. So this is new material. So preparation of amines via substitution. So here's a really neat reaction. If you take ammonia, so this is just plain old NH3, okay, and you treat it with iodomethane, it does an SN2 reaction on it, and then we end up with an alkyl ammonium ion, and then it deprotonates, right? You do a deprotonation with another equivalent of ammonia, and you end up with a primary amine, but this reaction doesn't work very well, okay? It says this is actually an efficient way to make a quaternary ammonium salt. So you could say here, this would actually be difficult to isolate. It'd be tough to isolate this compound, because what's going to happen is it's going to see another molecule of methylamine kicking around in the reaction mixture, and it's going to be like, hello, SN2, right? That's not really a good arrow, the first one. Should be on the carbon like that. There we go. So it's just going to do another SN2, and it's going to keep going and going and going. So it's kind of a runaway reaction, really. So monoalkylation is difficult because once you gain that alkyl group, then the lone pair becomes even more basic or more nucleophilic, right? Because you get electron density being donated towards the nitrogen via hyperconjugation. So it keeps alkylating and doing it over and over and over until you end up with a quaternary ammonium salt. Sometimes we call these quats. Okay, so you end up with a quat. And so we call this exhaustive alkylation. It's got a name. We call this exhaustive alkylation. It's like it can't stop alkylating after alkylating after alkylating. And we're actually going to exploit this reaction later on when we look at Hofmann elimination. So just wait in a little bit. We're going to look at Hofmann elimination. But just keep this in your mind until we get there. So if you're wondering, well, how would I make a primary amine then? Right? How would I make this if it's difficult to isolate just by doing an alkylation? Well, we have a few ways to do it. Okay, I'm going to teach you I think there's 3 different ways that it shows you how to do it in the book. The first one is an azide synthesis, and it uses sodium azide. So if you're unsure what azide is N3 with a -1 charge. So it looks like this. This is the Lewis structure of azide, like this. Yeah, so we have something that looks like this. There you go. So there's the Lewis structure of azide. So you can see that it overall has a negative charge, and so it can act as a nucleophile just like you think it would, and it can do an SN2 on an alkyl halide. I think I need another cup of coffee. There we go. So it can do an SN2 to make an alkyl azide. So this would be called an alkyl azide. And then you can reduce the alkyl azide by hydrogenation or lithium aluminum hydride reduction. The only problem with this reaction is that alkyl azides are explosive. So, you know, generally we frown upon doing explosions in the lab. We like to keep things safe around the lab. So there are better ways to make ammonia. So we could put here explosive. All right, so how else would we do it? Well, here's the mechanism of the formation of the amine when you react it with lithium aluminum hydride. So you end up losing nitrogen gas. I'm going to write on here, will not ask this mechanism, okay? It's not part of the content in ACS, so don't worry about this mechanism really. But you do have to know this new method of making a primary amine called the Gabriel synthesis. So Gabriel synthesis. We use this for the synthesis of a primary or secondary amine from this neat compound called phthalimide. How's that for a name for you? Phthalimide, okay? So what you do is you take phthalimide and you convert it into potassium phthalimide by treating it with potassium hydroxide. Now the pKa of this proton is around 8. I think in my notes I have 8.3, something like that. And of course the pK of water, I know you know that off by heart. Its pK is about 15.7. So the equilibrium is going to lie to the side of the water. So we deprotonate phthalimide to give us potassium phthalimide. And you can imagine that potassium phthalimide is a good nucleophile, right? You get a negative charge on the nitrogen, and so it can do an alkylation reaction. So let's take a look. We do an SN2 reaction, pretty easy. And of course, the same old rules for SN2 are manifest. SN2 works well with a methylamine, or sorry, a methyl halide or a primary alkyl halide. And so now that we've got this, we've got to find a way to liberate this part of the molecule, right? And then we want to leave this part of the molecule alone. Okay, so how do we get this part, the part that's in the black box? Well, there's 2 options. One option is to hydrolyze it with aqueous acid. So that's this route shown here. And that gives you this compound. This is called phthalic acid. So phthalic acid. And then it gives you the ammonium ion. And so you actually have to do a second step here. You'd have to treat this with sodium hydroxide, and that would give you the free base or the free amine like that. Or another option is to treat it with NH2, which is, if you remember, this is called hydrazine. We used it to make a hydrazone in chapter 19. And actually, this is a better reaction because you end up with the free amine And I think that if you treat this with aqueous acid, it takes a long time to heat that up and hydrolyze it all the way to the phthalic acid. So with that in mind, let's take a look at how we might use Gabriel synthesis to make each of the following compounds. And we know that when we're doing a Gabriel synthesis, we need some kind of alkyl halide. And for this compound, only the nitrogen comes from the potassium phthalimide. So all of this is going to come from our electrophile, which is going to be this compound. We could use the iodide, bromide, or chloride. And so I wrote the iodide. So here's what the steps would look like. First, you're going to take phthalimide. So in the book, he writes out all the steps. So he starts with phthalimide. Step 1 is to treat it with potassium hydroxide to make potassium phthalimide. Step 2 is to treat it with your electrophile, like this. And then the third step is to treat it with hydrazine. So H2 and H2, like that. And that is going to give you the product. So you would end up with the product in this case. All right, for the other one, again, the nitrogen comes from the potassium phthalimide, and all of this spinach is going to come from our electrophile. In this case, it's going to be a secondary alkyl halide, so it's going to look something like this. If you put chloride or iodide there, that's totally fine. And so we just regurgitate the exact same steps we did before. We started with phthalimide, and we treat it with a base, sodium hydroxide, and that makes, potassium hydroxide, and then that makes potassium phthalimide. Then we treat it with our alkyl halide, this is an aryl. Actually, I guess this is an alkyl halide technically. And then we treat it with hydrazine in the end. What the heck? I got peroxide on the brain. We treat it with hydrazine, and that will give us the desired product. Comme ça. There we go. So now we've made it all the way to reductive amination, which is a brand new reaction. So let's take a look here. So reductive amination is the way that we convert an aldehyde or a ketone to an imine, and then we reduce the imine to an amine. Now, you probably don't care about this, but I'll just tell you for interest's sake. Out of all the reactions that I did in Big Pharma, I did thousands and thousands and thousands of reactions, okay? But the one that I probably did the most was reductive amination. And the reason why, you can imagine that if I did it a lot, I did it a lot because it's really easy. It works really, really well. And what they have shown here is not the technique that chemists would use to do a reductive amination in 2023. This is just shown here to kind of show you the steps. Okay, the idea is that you take your amine, okay, in this case they used ammonia, and a catalytic amount of acid, that makes an amine, and then you can reduce an imine, and then you can reduce the imine via hydrogenation. Well, the good news is that now there's many, many reagents on the market that we can use to do a reductive amination where we do the reaction in situ. And what that means is that you form the imine and you do the reduction in place. So in situ is just Latin for in place. So you kind of do everything in one pot or in one reaction flask. Let me show you how you do that. What you do is, in order to reduce the imine as soon as it's formed, instead of using sodium borohydride, you use this less reactive form of it called sodium cyanoborohydride. The formula is, they should write it like NaBH3CN, like that. That's normally how it's written. Could make that a little prettier. There you go. So we use sodium cyanoborohydride, and I'm not going to go into how it mitigates the reactivity of sodium borohydride, but I'll just say it's less reactive because you have that electron withdrawing group, which stabilizes the negative charge, and then makes the borohydride more selective. Okay? And so what it enables us to do is, again, we can do our reaction in situ. We can put our amine, our acid, and our sodium cyanoborohydride all in the same reaction flask, and we can go directly from a ketone to an amine. So it's not magic, but what happens, again, is that you end up making the imine, right, in situ. Okay, you make the imine from ammonia and the catalytic amount of acid, and then in the second part, okay, so you do this, and then you do this, right? The sodium cyanoborohydride does the reduction in the second step. Give me a thumbs up if that makes some sense to you, reductive amination. Cha? Everybody with me on that? It's a very, very important reaction. Okay, I'm just going to erase some of these stars here so it's not confusing. Thanks, Audrey. Right, so you can see that you could use ammonia, right? Or, where's my pen? You could use ammonia, a primary amine, or a secondary amine. It will not work with a tertiary amine. It won't work with a tertiary amine as a reagent. But if we use ammonia, we get a primary amine. If we use a primary amine, we get a secondary amine. And if we use a secondary amine, we get a tertiary amine as our product. So just keep that in mind when you're practicing your reductive amination chemistry. But again, this is a very powerful reaction. I'm going to put a star on here, not because you have to memorize a mechanism or anything, but because I want you to appreciate how powerful this reaction is, right? Think about it. Most marketed drugs have nitrogen in them. So if we can find a way to incorporate a nitrogen that works really well, believe me, it's a good thing for chemists. So this question, 22.14, says, show two different ways of preparing each of the following compounds via a reductive amination. So if we look at B, on our nitrogen, we have a methyl group here, and then we have two propyl groups. I'll just circle one of them. So we could either start with everything except for what's in the blue circle, and then add the propyl group, or we could start with everything except what's in the, sorry, did I say red circle and then add the propyl group, or start with everything except what's inside the blue circle and then add the methyl group? So let's start by adding the propyl group. So the way that we would do that is we would start with this amine. So we would start with this secondary amine. So that would be N-methyl N-propylamine. And then what we're going to do is we're going to treat it with propionaldehyde. So maybe I'll try to write it the way that they would have it in the book. So what you're going to do is you're going to take the 3 carbons that are in the red. No, I didn't mean to do that. You're going to take the 3 carbons that are in the red circle, and you're going to draw the aldehyde of that. There, that's how they present it in the textbook. And what you're going to do is you're going to treat it with the amine, okay, like this, okay. So there's your amine. Then you need a catalytic amount of acid and sodium cyanoborohydride. So sodium cyanoborohydride, and that's going to do the reductive amination, and that's going to give you the product. So I'll draw the whole dang thing out like this, okay? The other option would be to start out with formaldehyde. So if I start with what's in the blue circle, so I'll start with formaldehyde. Here's my aldehyde, okay? And I'm going to treat this with dipropylamine. So we'll put here dipropylamine, so that would look like this, okay? And then we're going to treat that with a catalytic amount of acid and sodium cyanoborohydride. And that will also give us the product like that. So what I would like to do now is take a short break, and I would like you to give this one a try and see if you can come up with a way to make this by breaking this bond or this bond. So we'll try C after the break. And then I'd also like you to give a shot to see if you can make methamphetamine. It says methamphetamine is used in some formulations for the treatment of ADD and can be prepared by reductive amination using phenylacetone. So phenylacetone, if you draw acetone, well, maybe I should draw acetone first. If we draw acetone and then we put a phenyl group on it, that's phenylacetone. And methylamine, well, that's methylamine. It looks like this. If you do a reductive amination with those two, you end up with methamphetamine. So I want you to give that a try as well. So I'll get you to try both of those. And then after that, what we're going to do is we're going to review all the ways that we learned how to make a primary amine. We covered the Gabriel synthesis. We covered Azide synthesis. And then we covered reductive amination. Now, reductive amination is the most powerful of all 3 of these, but why, and I've gone over this a few times in class, why do chemists have to know more than one way to do the same reaction? It's because a lot of reactions are going to be substrate specific. It depends on your reactant, how well one reagent is going to work versus another. So we've covered all of these. We've talked about how to do reductive amination. And if we do reductive aminations, we can keep adding our groups to our nitrogen. And then once we get a tertiary amine, we can do an alkylation to make a quaternary ammonium ion. So what I want us to do as well after the break is to come back and try and do a couple of these problems. Maybe we'll just do one. It says using ammonia as your only source of nitrogen, show how you would make, just try this one here, and maybe we'll try B if we have time. But I don't want to spend too much time on these synthesis problems because our next class is entirely devoted to this chapter. So what we'll do is we'll take another short break, and then we're going to come back and we're going to tackle question 22.14, 22.15, the synthesis of crystal meth, and then we're going to try 22.16a, and then we'll see about B. And then after that, we're going to talk about acylations. And I know this is a reaction that you know very well because we covered this reaction in chapter 20. We talked about taking an acid chloride and reacting it with an amine. Everybody remembers that. And so we're going to talk about why you would acylate an amine and what it's useful for. It actually is useful as a protecting group. So we're going to add that to our list of protecting groups that we've learned in Chemistry 3111. So again, when we come back, we're going to tackle these practice problems starting with 22.14c.